In this video, I want to explore some different examples of finding the slopes of tangent lines, finding equations of tangent lines, and finding the derivative of a function. Okay, so those are all very related things. They're almost all the exact same, but of course the derivative is a little bit more wide spectrum, right? It doesn't necessarily zoom in on a specific value of c. But first here, let's go back and find the slope of the tangent line to a function. Here I've got 2x minus 3 at c equals 2. So I'm looking at a specific point that I'm finding the tangent line of. Here's my formula from the previous video. I've got f of c plus delta x minus f of c over delta x, and then a limit as delta x approaches 0. Okay, so what I need to evaluate this limit is I need f of c plus delta x, okay? So what I do is I take my function and I plug in c plus delta x. So c is 2, delta x is delta x. My function is 2x minus 3. So in for x, when I plug in c plus delta x, I get 2 times 2 plus delta x, all then minus 3. Okay? I want to simplify this a little bit. I can distribute that 2. I end up with a 4 plus 2 delta x minus 3. And of course, 4 minus 3 is a 1. So I've got 2 plus delta x plus 1. That's going to go in the numerator where I've circled that f of c plus delta x. In my numerator, right there. I'm going to subtract from that f of c. What is f of c? It's f of 2. Plug in 2. 2 times 2 is 4, minus 3 is 1. So that 1 is going to go in there where f of c should be. All divided by delta x, and then send delta x to 0. So just about every time we do this, there's going to be some sort of cancellation. In fact, there's probably going to be multiple cancellations that happen. The first one I see here is plus 1, minus 1. Those disappear. I'm left with 2 delta x divided by delta x. When you're doing these, there should be no extra terms, no constants, no anything. You should have delta x's in every term in the numerator. You've already got one in the denominator, right? But you should always have one in every term in the numerator. This example is really straightforward, and I end up with just a delta x up there times a 2. I get a similar cancellation. So the limit then, as delta x approaches 0, is taken of 2, and the result is just 2. Okay? Think about the kind of function you have. I've got a linear function. The slope of a linear function is always 2. Is always 2. So there's no reason I should expect some different value to find the slope of a tangent line of a linear function to be different than the slope of the function itself, right? Things are making sense, right? If you can sketch the graph of 2x minus 3 and draw a tangent line anywhere, and you're going to get a slope of 2. Okay? I didn't really have to go through this process to get that information, right? But just going through and kind of showing how that limit works, because we're going to get some trickier examples here. F of x equals x squared plus 1. I want to find the slope when x is 0. Okay? So same formula. Take the derivative basically at 0. I'm evaluating this limit, and again I need f of c plus delta x. So f of c in this case is 0 plus then delta x. F of c plus delta x is 0 plus delta x, and I plug that in for every x in my function. Okay, so every x here is x then squared, and I get a plus 1 from this extra 1 here. Subtract what I get when I plug in 0 to my function. 0 squared is 0 plus 1 is a 1, and I'm going to subtract that. Okay. So the format, the kind of layout of each one of these examples is going to be basically the same, right? I've got this limit that's going to find the slope of the tangent line no matter what function I have or what x value I'm talking about, okay? So I'm ready to make some cancellations here. Plus 1 minus 1, those disappear. And when I have a 0 in the numerator there, plus delta x, that 0 I can just get rid of. delta x squared is left divided by delta x. Easy enough. Delta x's cancel. I can cancel one of them in the numerator, and that leaves me with the limit as delta x goes to 0 of just delta x, which is, of course, 0, right? Delta x is approaching 0 as delta x approaches 0. Okay, so what this gives me is the slope to my function, x squared plus 1, at x equals 0. Okay, this is, again, really the slope of the tangent line as well, right? So those two are the same thing. I use slightly different terminology to talk about the same exact thing. I've got the slope of the tangent line. What if I want, what would the equation of that tangent line be? What is the equation of the tangent line? So I'm looking for a specific equation here. I should be able to graph the result, and it should show what the tangent line looks like when x is 0. Okay? I can use one of the two formulas here, mx plus b, or y minus y1 equals m times x minus x1 with the slope of 0, right? I found m to be 0, and the point I'm looking at is when x is 0, y would be 1. And I get that by plugging c, 0, into my function. This 1 is really f of 0. Okay? I can use either of those two formulas. Of course, the equation of the tangent line should be linear. It's a line, right? So I'm going to use this second equation here. This is my point slope form. And I set that up as y minus y1. Y minus 1 equals m, 0, times x minus x1. When all is said and done, 0 times x minus 0 is nothing, it's 0. So I got y minus 1 equals 0. That's going to result in a y equals 1. That is the slope of the equation of my tangent line. It's just a horizontal line at 1. I want to sketch this just quickly here. Let's draw a set of axes, and my equation there, x squared plus 1, y equals 1, is that horizontal line with a slope of 0 right at 1. Right? So really, that tangent line there has a slope of 0. Cool. Maybe a little not interesting, maybe interesting, but it's definitely doable. If I was looking for the slope somewhere else, I could find it, just change c to be whatever value, take that limit, and you've got it, okay? So let's switch gears just a little bit. I want to find maybe now what I call the derivative of my function, okay? The derivative of y equals x cubed. I'm no longer looking at some specific x value, right? I'm no longer looking at c, I'm looking in general. What's the slope of that graph at any point, okay? And I'm going to use my equation here. And instead of c plus delta x, again, I've changed it to x. It's general. So I set the same kind of thing up. In this case, my function is x cubed. So when I find my derivative, that limit here, I've got to plug in x plus delta x, right? So I've got x plus delta x cubed minus f of x minus x cubed over delta x. If you try to evaluate this limit right now, you're going to get 0 over 0, okay? So I go through kind of my limit techniques. I can actually just expand this cubic, right? I can expand and FOIL that 3 times, okay? I'm going to do it rather quickly here. This is then the limit as delta x goes to 0. That's going to give me x cubed plus 3x squared delta x plus 3x times delta x squared plus delta x cubed, right? That's what happens when I cube x plus delta x. So all that's left then is my minus f of x, my minus x cubed, and all divided by delta x. Right? So this was a relatively straightforward one. It takes a minute to expand that binomial there, that x plus delta x, and raise it to the 3rd power, but it's definitely doable. I notice that I've got x cubed minus x cubed. Those are going to cancel. And then everything else here is going to show up in the numerator of my limit. 3x squared delta x plus 3x delta x squared plus delta x cubed. Okay. Now I also notice that each one of the terms in the numerator has a delta x in common. That should happen. If that doesn't happen when you're finding a derivative, then you've made some mistake along the way, right? Maybe you factored or expanded or multiplied by a conjugate wrong. Something happened along the way that made things not work out. Each term in the numerator's got a delta x. I'm going to factor that out. Get a delta x times 3x squared plus 3x delta x plus a delta x squared, again, all divided by delta x. That's got to happen. Otherwise, when delta x goes to 0, I'm going to get 0 over 0. And to curb that, what's going to happen is these delta x's are going to cancel, and I'm left with everything in parentheses there. Now, as delta x goes to 0, I can actually evaluate this limit. Both of these terms here, the middle two, are going to 0, and all I'm left with is a 3x squared. So we say 3x squared is the derivative, dy dx, of my function. That's the slope of the tangent line. The slope of y equals x cubed at any point is 3x squared. Okay? Cool. So if I wanted the slope when x is 0, I can simply now plug in 0. I don't have to go through the entire limit process again. I've got the derivative, I've got the slope of my function at any point. Okay? So we see the power of this. I don't have to evaluate a limit for each slope that I want to find. I've got a formula that will do it for me. Cool. Let's do another example. Find f prime of x, the derivative, for the square root function, square root of x. Okay, same exact process as before. I want to make a note here. Very frequently, what you'll see is this derivative formula, this limit, but instead of delta x, what a lot of people use is h. Okay, and it might be a little bit less confusing. I don't know. It's kind of up to you what you use. The book uses both. A lot of people use both. So I just want you to be aware that you will also see the derivative in its limit form written with h instead of delta x. So I'm going to use that format for this example. It's not really going to feel any different. I'm just going to write h's instead of delta x's. Okay. So I find f of x plus delta h, and I write that in my limit. That whole thing is going to be my derivative. So in for x of my function, I plug in x plus h, okay, for f of x plus h. I subtract f of x, I subtract that square root function, and I divide by h. Again, as h goes to 0, I'm going to see something that looks like 0 over 0 here, okay? So in a situation like this, from before, we were able to evaluate limits like this before. You might have had an x plus 2 minus square root of x divided by, h as h goes to 0. Or something. You might have had something similar to this, and what we did is we multiplied by the conjugate. Okay? That format does not change here. So I've got the exact same kind of limit technique as I had before. I'm going to evaluate this limit multiplying by a conjugate. So when I do that, my limit becomes, in the denominator, I'm just going to slide that factor of the conjugate over. I'm not going to distribute anything because I'm hoping that h in the denominator is going to cancel. In the numerator, I am going to FOIL, and what I get is a difference of squares. I've got square root of x plus h squared is just x plus h, minus square root of x squared is just an x. Okay, so when we've got those radicals split up like that, that's an indicator that we're going to look towards the conjugate to help. I see that x minus x cancels, and I'm left with only an h in the numerator, and that's ideal. Again, just like I said in the previous slide, I want a delta x in every term in the numerator. I want an h in every term in the numerator. There's only one term in the numerator, it is h, and I can cancel that with the h in the denominator. If those were delta x's, the same thing would happen. This is what I'm left with. And now I can take a limit as h goes to 0. I get 1 over square root of x plus square root of x is 1 over 2. I can add those together. I get 2 square root of x's, 1 over 2 square root of x. This is my derivative. Okay, and I just want to make a note that all the same limit techniques still apply when I'm finding derivatives. All the same techniques: multiplying by a conjugate, factoring and canceling, expanding, using a common denominator. All of those things are going to stay here. And that's why we go through them before this, so that we're ready to take derivatives and evaluate these specific types of limits here. I want you to pay attention to this derivative and notice the denominator, right? I can describe the domain of this derivative, and that's going to be an important bit of information for us. The domain of f prime here is all positive x's, right? I can't have square root of 0 in the denominator there because I would be dividing by 0. So my domain of the derivative is all positive numbers, positive real values. But what that indicates is that f is actually differentiable then for the domain of the derivative for when x is positive, right? So what that says is that my function, the square root of x, is not differentiable when x is 0 or negative, of course. I actually have what we would call a vertical tangent. We talked about that a little bit in the last video, a vertical tangent at x equals 0. And that's because that limit is going to give me a positive or negative infinity or something like that. I'm going to have a vertical tangent at that point. Okay? So that leads us to kind of some interesting discussion. We know there are places where the derivative might be undefined. There might be places where the derivative doesn't exist, or where this limit results in a plus or minus infinity, where the limit doesn't exist. This example I'm going to go through rather quickly, x to the 1/3 or the cubed root of x. Okay? What we've got here is a continuous function. There are no domain issues for the cubed root of x. I can plug in negatives to the cubed root of x. There's nothing to worry about. However, when I take a derivative here, I'm going to go through it a little quickly. This limit as x goes to 0 of f of x minus f of 0 over x minus 0. So I'm using that previous form, and I'm doing it for a reason, because I'm looking specifically when x is 0 here. When I do this, this is going to be, again, the slope of my function at x equals 0. I crunch the numbers here, and I end up with f of x is the cubed root of x minus f of 0 is 0. Cubed root of 0 is 0. So I've got x to the 1/3 in the numerator and just an x in the denominator. When I simplify, I end up with the limit as x goes to 0 of 1 over x to the 2/3. That limit is infinite. That's an infinite limit. The denominator is squared. There's a 2 in the exponent, right? It's squared. So whether I approach x or approach 0 from the left or from the right with negatives or positives, they're being squared. But that 0 is in the denominator. I'm approaching a number over 0. I've got infinite there. I've got an infinite limit. So what that indicates is that f of x here has a vertical tangent line at x equals 0. And more importantly, that the function is continuous at 0, but it is not differentiable. Just because a function is continuous, this is important, just because a function is continuous does not mean that it's differentiable. Okay? And we've shown that. We've taken a derivative at 0 and we get undefined. We've got a vertical tangent. I cannot actually take a derivative at that point. The limit does not exist. But my function's continuous. Okay? What this leads us to is, kind of an opposite scenario. The differentiability implies continuity, and there's a theorem that shows this. If f is differentiable at x equals c, then we can say that f is continuous there. So what we've got is that the limit exists, that difference quotient, the limit as x approaches c would exist, and we're also able to show that that's the same as the function value at that point. Okay? The important thing to note here is that this that this theorem does not work in reverse. okay? I can't go the other way with this limit. Continuity does not necessarily imply differentiability, okay? Refer to the previous slide. I had a continuous function that was not differentiable at 0. However, if I've got a function that's differentiable everywhere, it's continuous everywhere. So it's a little abstract, but I wanted to emphasize this. It's an important idea that we'll kind of talk about, throughout the remainder of the semester. But just some derivative examples, and also kind of highlighting that finding the slope at a point, finding the slope of the tangent line at a point, finding the slope of a curve, and finding the derivative at a point are all the same thing. Okay? Thanks for watching.